In today's lab, we're going to be using ICs, or integrated circuit chips. It's a great introduction to electrical engineering. We're going to be designing and building circuits. There's no coding involved. Today we're going to be using the logic gate chip. It has inputs and outputs that take in and out voltage, similar to an Arduino, but there's a preset series of rules and there's no coding involved. In this gate, the triple input AND gate, there's three inputs, A, B, and C, and all have to have voltage in order for voltage to come out at the output. There has to be voltage at A and B and C in order to get voltage at the output. Another common type of chip is an OR gate, which only requires voltage at A or B or C in order to get voltage out at the output. They also come in dual input, triple input, quad input, depending on what you're trying to design. So let's take a look at the circuit and how they work. The way you know which chip you're using is to Google the serial number on the chip. The easiest way to see that is usually, if you can't do it with your naked eye, is to take a picture of the chip, usually with a flash, zoom in. Googling the chip will show you what it is, what it does. Google Images the chip number with the word pinouts will pull up an image of what pins you're going to be using to connect things to your chip. In this case, we could see the pinouts for the triple input AND gate. We're going to be using the gate on the bottom left. So pins 3, 4, and 5 will be our three inputs, and pin 6 will be our output. Okay, let's talk about our circuit. The Arduino here on top is just being used for power, 5 volts and ground. There's no code and all the data pins are empty. The circuit here on the right is our triple input AND logic gate. Don't forget, you do need 5 volts and ground to power the chip. If you mix those up, the chip could burn up, might be broken. We're going to be using the AND gate on the bottom left-hand corner. So pins 3, 4, and 5 in green are our inputs, our three inputs. And pin 6 is our output going here to an LED. Don't forget to connect it also to ground. In this case, since all of our devices are being powered by the same Arduino board, all of our grounds are already connected. For our first input, we're going to be using a simple button circuit. I'll go over it really quick. We have 5 volts going through the button, through a resistor, and into ground. What that means is when the button is not pressed, the entire right side of the circuit is just a black wire and a resistor. There is no voltage in it. It is low or ground. When I press the button, the 5 volts then jumps across the button into the right side of my circuit. We'll go through this green wire and turn that input high. So when the button's pressed, the input becomes high. My second and third inputs are from this Arduino running the blink code. So pin 13 is just blinking high, low, once a second. That's my second input. And my third input is just hardwired to 5 volts. What that means is that my third input is always going to be high. Now, it's important to note that just because your pin has nothing connected to it doesn't mean that it's low or ground. You have to actually connect your pin to a ground source or a zero voltage source in order for it to be low. The reason is there could be residual voltage. The chip might be retaining the last state that it was in, or it might even be affected by static electricity internal to the chip. So in order for the chip to be low, we have to connect it to a ground source. So my first input is a button. My second input is pin 13 blinking, high, low, and my third input is 5 volts, always high. So if I turn on input number 1, so whenever input 1, input 2, and input 3 are all high, my output, my LED, lights up. That happens once a second. When my button is pressed, it's a latching button, so it stays pressed all the time, similar to a switch. This pin is always high. When pin 13 blinks, I have all three inputs high, and I get a high on my output. If I unlatch the button, I might have 2 inputs high, but I don't have all 3 high. Since it's an AND gate, all 3 need to be high at the same time. Now, all logic gates come with something called a logic gate truth table. So for the logic gate circuit here on the screen, we have an AND gate and an OR gate, both with dual inputs. We could try and complete the logic gate truth table for this particular circuit. So looking it over, we could see since input 3 goes into an OR gate, anytime input 3 is high, we're automatically going to get a high output. So we could automatically have a high output anytime input 3 is high. The other time we'll get a high output is anytime pins 1 and 2 are high. If 1 and 2 are high,
the AND gate will output into the OR gate. So anytime 1 and 2 are high, that's over here. And that's the only time. And the rest of the time, our circuit will be low. So this is a truth table for this particular logic gate circuit. Now, how is this useful? What's the point of this? In actuality, we do the truth table logic gate circuit in reverse. We start with our truth table. So in this case, we have a school air conditioning smart system, and we want to try and figure out when to automatically turn on and off the air conditioning. So our 3 inputs, instead of calling them 1, 2, and 3, we're going to call them the outside temperature if it's hot, whether or not it's a school day or a non-school day, and whether or not students are present in the building. So let's start with when students are present. Anytime students are present, we're going to want to turn on the air conditioning. And now we'll also turn on the air conditioning, not necessarily if it's hot outside and not necessarily if it's a school day, but if both of those happen. If it's hot outside and it's a school day. And when does that happen? That happens over here. It's hot outside and it's a school day. Here it's hot outside, but it's not a school day. Here it's a school day, but it's not hot out. And here it's not hot out or a school day. And we'll start with our truth table, and then we'll design our circuit to solve all the conditions that we're looking in our parameters. So first we figure out what we need, we set up our parameters, and then we design our logic gate circuit.
Now you might be wondering, what's the point of all this? Why not just use an Arduino, write a few lines of code, and create the simple game? The answer to why we use chips is 2 reasons: simplicity and cost. Once you have your circuit dialed in and designed correctly, it's so much more reliable and easy to recreate using chips rather than a whole coding system. And the main reason that drives a lot of engineering is cost. An Arduino, a microcontroller, coders could cost $10, $15, $20 per set, while an IC chip might cost 1 or 2 cents. So that's an important factor when you're taking into account, especially when you move into manufacturing side of things, that an electrical engineer has to decide, am I going to be using straight chips or am I going to be using coded microcontrollers?